Welcome to the video lecture on crystal field theory. My name is Dr. Jinesh. I am from Department of Chemistry, Ramaya University of Applied Sciences. In today's lecture, we will study about Introduction to Crystal Field Theory in Coordination Compounds. We will study about DD splitting. Color of the coordination complexes will be discussed. Magnetic properties of coordination complexes will be discussed in this video lecture. All of you studied crystal field theory in your PUC. So before starting my class, I would like to bring those points you studied in your PUC. In a coordination complex, central metal atom or ion along with ligands are present. It assumes that the attraction between the central metal and the ligands in a complex is purely electrostatic. The transition metal which forms the central atom in the complex is regarded as a positive ion of charge equal to its oxidation state. This is surrounded by negative ligands or neutral molecules which have lone pair of electrons. If the ligand is a neutral molecule such as ammonia, the negative end of the dipole in the molecule is directed towards the metal ion. And when you studied CFT in your PUC, you have taken few assumptions. They are: ligands are treated as point charges. The d orbitals on the metal all have the same energy in the free atom. So we can say the d orbitals are degenerate orbitals. However, when a complex is formed, the ligand destroys the degeneracy of these orbitals. That is, the orbitals now have different energies. Now we have to discuss this degenerate and non-degenerate concept in CFT. In an isolated gaseous metal ion, the 5d orbitals do all have the same energy and termed degenerate orbitals. We know the names of these 5d orbitals: dxy, dyz, dxz, dx square minus y square, and dz square. But when the ligand approaches, the degenerate nature of d orbital loses and becomes non-degenerate, means they will have different energies. How is it possible? To understand this concept, I will give you a situation. 5 of my students wanted to go to Goa for a pleasure trip, but all of them had no money. So what they did, they had taken loan from a moneylender. Look at him. He is so strong and big. By taking that money, they went to Goa, spent the entire money, enjoyed a lot, and came back to Bangalore. They forgot to pay the money back to the dangerous moneylender. As usual, it's quite obvious. One day, these students were playing football, and in between, they saw a terrible thing is happening. All of them had seen that the moneylender was coming to the football ground. All of them became scared. They knew that something bad is going to happen. If they scared means their energy went up high. When the moneylender reached near to the football ground, they realized that 2 of them are in the same direction to that of the direction of moneylender. Those 2 students became too much scared because they understood that first he is going to catch them and beat. They became super scared and their energy went again high. In the same time, the other 3 students understood that the moneylender is not coming to their direction. They became now little bit relaxed because they knew by the time the moneylender catches them, the other 2 guys, we can escape. So they got little bit relaxed. Relaxed means their energy came down. Now you see, all of them took money, but now 2 of them are super scared and the other 3 are somewhat relaxed. So now 2 groups of students are formed with the different scared moods, or in other words, different energy levels. Their difference in energy depends on how strong the moneylender is. If the moneylender is really big and strong, then the difference in their energy will be higher. If the moneylender is a weak and sweet guy, then the energy difference will be less. Now we can club this trip to Goa situation with the DD splitting in octahedral complexes. In the first step, consider only the central metal atom or ion where no ligands nearby. In the absence of ligands, the isolated central metal atom or ion has degenerate d orbitals. All d orbitals have same energy at this point. The lobes of dx square minus y square and dz square point along the axis x, y and z, and we call these orbitals as Eg. The lobes of the orbitals dxy, dxz and dyz point in between the axes, and we call them as T2g orbitals. The terms Eg and T2g are symmetry elements, and the meaning of these symmetry elements you will study in the coming semesters. Now imagine, to this central metal ion or atom, ligands are approaching. So like in the example of trip to Goa, all these 5d orbitals will increase their energy as in the energy diagram. But when the ligands approach very near to the metal atom, and from the octahedral ligand field, the Eg orbital's energy will be increased again and the T2g orbitals will be lowered at the same time. Because in octahedral ligand field, the ligand approaches along the axis x, y, z. So Eg orbital's energy will increase further, similar to our trip to Goa example, and the T2g orbital's energy will be lowered. Now we got two sets of d orbitals with a difference in their energy. The splitting of d orbital based on their energy is known as DD splitting, and the energy difference is known as crystal field splitting energy CFSE. Here the complex is octahedral, so that energy difference is named as delta octahedral. Now similar to the Goa trip example, if the ligand is strong, then this delta octahedral will be larger. If the ligand is weak, then this delta octahedral will be smaller. In this diagram, the average energy level is pointed out as the Barry center. From the Barry center to Eg orbitals, the energy difference is plus 0.6 delta octahedral. From Barry center to T2g orbital, it is minus 0.4 delta octahedral. Now, how can we arrange the electrons in the d subshell? If delta value is lower, then the sequence is like this. After the entry of electron to T2g orbital, then the electron can go to fill the Eg orbitals with one electron each, because delta value is smaller. After the entry of electrons to the T2g orbitals, then the electrons can go to fill Eg orbitals with one electron each. After that, second electron can be filled in T2g orbital followed by Eg orbitals. So with weaker ligands, generally this will be the trend. In this case, now you can see chance of paramagnetic or high spin complex character will be more for the complex. If they are high spin complex, then the magnetic moment will also be higher. You know the equation if you know the number of single occupied orbitals and then the calculation of magnetic moment. If delta value is higher, then the sequence will be like this. After the complete filling of T2g orbitals, then only the Eg orbitals will be filled up because the energy gap is too high. This will happen generally with strong ligands. Therefore, more chance for the complex to become low spin complex or diamagnetic. We will study the examples of these in the next video. Now we will see the case of tetrahedral complexes. Here only 4 ligands and they won't be approaching along the axis in the tetrahedral ligand field. So in this case, the splitting happens in the reverse way as that of octahedral complexes. Here, T2 orbitals, important things to note T2g, will have higher energy compared to E orbitals. And the energy difference, that is delta tetrahedral, will be only 4/9 of delta octahedral if both the metal atom and the ligands, same ligands, are involved. That means when the electrons are filled in the d orbital, there is a great chance to enter the electrons in the orbital similar to the following manner. First, 1 electron each in E orbitals, then 1 electron each will be filled in T2 orbital, then the selected electron will be entering into E orbital followed by T2. Now chance will be more for high spin complex. Now I gave you a clue to solve one. In today's class, we will study about the color of the coordination complexes. We know that generally coordination complexes have colors. With the help of an example of an octahedral complex, we will study the reason behind the color of the coordination complexes. For example, hydrated solution of titanium H2O6 3+ is violet colored. Why? In titanium complex, the oxidation state of titanium is +3. Electronic configuration of titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Electronic configuration of titanium 3+. Here 2 electrons will be removed from 4s orbital and 1 electron will be removed from 3d orbital. So the final electronic configuration for Ti3+ is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. Means here the metal ion is at a d1 configuration. Why it is known as d1 configuration? Because only 1 electron is present in its outermost d orbitals. In the last class we studied in the presence of ligand, the d orbitals, its degeneracy will be lost and will be splitted into 2 sets of orbitals, T2G and EG, and their difference in energy is called delta octahedron. So in normal state, the electron, the d1, that electron in the d orbital will be in T2G orbitals. But if you pass a light or a radiation through this complex, then this electron will absorb energy from the given radiation, and that energy will be utilized for the excitation of that electron from T2G to EG. Here you can see at ground state the electron was in T2G. After the absorption of light, then the electron is now shifted to EG. The complex absorbs light of the correct energy to promote the electron from the T2G level to the EG level. D1 configuration in octahedral complex. How much energy is required for this transition? We can calculate it by using UV spectroscopy by taking the electronic spectrum of the complex. Here you can see the electronic spectrum of the titanium complex. You can see a peak in the range of wave number of 20,300 centimeter raised to -1. That means when we pass UV visible light through this solution of this complex, the complex absorbed a portion of the light spectrum at around wave number of 20,300 centimeter raised to -1. For what purpose the complex ion TiH2O6 3+ absorbed the portion of a UV visible light of wave number 20,300 centimeter raised to -1. This is for the excitation of the electron from T2G to EG orbital. So the energy is taken from the given light and the energy is utilized for the excitation process. Now, whether that energy is equal to delta octahedral? Answer is yes. The energy required for the excitation is equal to delta octahedral. So UV visible spectroscopy is an easy method to determine delta octahedral. 1 kilojoule per mole is equal to 83.7 centimeter raised to -1 wave number. So in this case, delta octahedral will be 20,300 divided by 83.7, that is 243 kilojoule per mole. So I am comprehending all these statements. At a ground state, for a D1 configuration complex, the electron will be at T2G orbital, but when it gets enough energy, that energy will be utilized by the electron from jumping from T2G orbital to the EG orbital. at excited state. So the complex absorbs light of the correct energy to promote the electron from T2G level to the EG level. Now how color is absorbed? The complex absorbed light in the range of 20,300 centimeter raised to minus 1 wave number. In the visible spectra, this range, this 20,000 range is for yellow to green. That means the complex absorbs the light in the yellow and green region. The remaining light, except yellow and green, the remaining light will be transmitted through the complex. We can see only the transmitted light. So the transmitted light will be the combination of the remaining colors of the visible spectra, and we call that combination as complementary color. So we will be seeing only the complementary color of yellow and green. Here the complementary color is red-violet. That's why the complex was in red-violet color. Here I am giving you one table where which color is absorbed by the complex and the color of the complex. For example, if a compound absorbs light in the region of yellow to green, then it will be appeared as red or violet. If a complex is absorbing a color in the range of orange, then it will be appeared as blue. If a compound absorbs in the range of blue in the given radiation, then the complex will be appeared as orange. Whether all D1 configuration shows same color? No. Based on the energy of the transition from T2G to EG, color will be observed. That means if that energy difference is different, then the color also will be different. The energy gap, which is delta octahedral, depends on the following factors. Nature of the ligands, means if the ligand changes, color also will change. The charge on the metal ion. For example, you have chromium ion, Cr3 plus, it will show one color, Cr2 plus, it will show another color. So charge of the metal ion changes, color also changes. Now whether the metal is in the first, second or third row of transition metal, these are the factors which changes the delta octahedral. So these are the factors which changes the color of the coordination complexes also. For example, here you see I have given 4 different complexes of chromium with different ligands, and you can see they absorb light at a different wave number. So these different compounds show different color. You can see that. Now I have given, for example, CrNH363 plus, ammonia based ligand with chromium metal ion, it show violet color. Chromium, another example, chromium with the OH hydroxyl as the ligand shows green color. Cobalt with the H2O shows a pink color. Cobalt with the ammonia is like a grey color. Copper with the ammonia and water, that's a dark blue. Copper with the water, light blue. So in this class, now we will study the magnetic properties of coordination compounds. Magnetic moment can be measured using a Gouy balance. You can see the photo of a Gouy balance. Magnetism of a sample is measured by the molar magnetic susceptibility Chi-m, which is related to the magnetic moment mu by the relationship mu equal to 3k by n0 into Chi-m into t. Means mu depends on the Boltzmann constant k, n0 Avogadro number, Chi-m molar magnetic susceptibility, and T temperature in Kelvin. But here we assume that the magnetic moment arises entirely from unpaired electron spin, then the spin only formula will be used, and that equation is mu s equal to root of n into n plus 2, where n is the number of unpaired electron. So here we consider the magnetic moment arises only from the electron spin. We are not considering other factors which influences the magnetic moment. This gives reasonable agreement for the complexes of the first row transmission metal. So this equation is mainly valid for the D block elements, especially in the first row of transmission metals. In second row and third row, there will be a large deviation in the experimental value and the calculated value in the magnetic moment. The number of unpaired electrons and the magnetic behavior can be explained with the help of crystal field theory. We will study the magnetic behavior with the help of examples of cobalt ions, CO3 plus based coordination complexes. For example, CONH3 3 plus is an octahedral diamagnetic complex ion, and COF6 3 is an octahedral complex with a paramagnetic nature with a measured magnetic moment value of 5.3. Explain the magnetic behavior of these two examples. So similar complexes with the different magnetic properties. Why they are having different magnetic properties, we are going to explain. In CONH3 3 plus, the central metal ion is cobalt 3 plus. Cobalt 3 plus contains 6 electrons in its D subshell. So the electronic configuration is a D6 configuration. So D6 configuration means 6 electrons should be distributed in the d orbitals. Now we know that when the ligand approaches to the central metal ion, the d orbitals degeneracy will be lost and the orbitals will be splitted into two T2G and EG. T2G and EG. And the energy difference between them, here it is delta octahedral. Now you can see the coming ligand is ammonia, which is strong, so the electrons are filled based on the internal pairing. Internal pairing means entire T2G should be filled first, then only the electron will go to EG orbitals. So here it is a D6 configuration, so 6 electrons. So all 6 electrons will be occupied in T2G orbital and there will not be any electrons going to the EG orbital. Now if you see, there are no single occupied d orbitals, so this complex is diamagnetic and the magnetic moment value is 0. Now you know that why CONH3 6 3 plus shows diamagnetic property. In the case of cobalt COF6 3 here also cobalt oxidation state is 3 plus and it is in D6 configuration, and when the ligand approaches they will be splitted into two sets of orbitals T2G and EG. Now you can see the incoming ligand is a fluoride group. So fluoride compared to ammonia, that is weak. So in this, if the ligand is weak, the electron sharing or electron filling will not be through internal pairing or the internal pairing will not occur. So what happens? Initially 1 electron each to T2G orbital, then EG will get 1 electron. Then if any surplus electrons are there, then it will be filled based on the Aufbau principle. Now total 6 electrons are there because it is a D6 configuration. 1 electron to T2G, 1 electron to T2G, 1 electron to T2G, then 1 electron to EG, 1 electron to EG. Now 1 electron left, that will go to T2G. Now if you see the electron filling, you can see that there are 2 single occupied d orbitals in T2G and 2 single occupied d orbitals in EG. So the total number of single occupied d orbital is 4. So this complex is paramagnetic and the magnetic moment value E can be calculated as mu equal to root of n into n plus 2, that is root of 4 into 4 plus 2, and the value is 4.90. Now we know that why COF6 3 is a paramagnetic compound. Now we will consider a tetrahedral complex. So here we consider the central metal ion is CO2 plus. CO2 plus means it will be a D7 configuration. In D7 configuration, and we know that the splitting is happening in a different way. Here the 5d orbitals will be split into two. One is E and T2. Here E orbitals have lesser energy than T2, and the energy difference between E and T2 normally we will call it as delta tetrahedral, and this delta tetrahedral value, if you compare with octahedral complex, it will be less only. Now it is a D7 configuration, so 7 electrons should be filled. So first one electron each should go to E orbitals, then T2 will be filled one each, then again E will be filled. So here there is no internal pairing. Now you can see here 3 single occupied d orbitals are there, so the complex is paramagnetic, and magnetic moment we can calculate as root of n into n plus 2 equal to root of 3 into 3 plus 2 equal to 3.87. So here there is no internal pairing, and you can do one thing also. If there is an internal pairing also, I don't think there will be any difference in the electron filling process. So in D7 configuration, irrespective whether it is a strong ligand, whether it is a weak ligand, this is a paramagnetic compound. Now in square planar complexes, you can see you cannot see so many stable square planar complexes. Only very little square planar complexes are there, and most of the square planar complexes are in D8 configuration. You can hardly see 1 or 2 D9 configuration square planar complex. Most of the square planar complexes are D8. For example, Ni2 plus based complexes, Cu3 plus based square planar complexes, everywhere the configuration is D8. So here we are considering a D8 configuration to explain the magnetic properties in square planar complexes. So in square planar complexes, the 5d orbitals are split into 4 different orbitals with different energy. dxz and dyz, both of them have same energy. dz square is having a slightly higher energy than that of dxz. Then dxy, another orbital with a slightly higher energy than that of dz square, and dx square minus y square, and the difference in energy between dx square minus y square and dxy is very high. So the energy gap between the dx square minus y square and dxy is large. Now we have to fill the electrons. Total 8 electrons are there, and that they should be filled, 1 in dxz, 1 in dyz, 1 in dz square, 1 in dxy. So totally now 4 electrons used. Then the remaining 4, again 1 in dxz, 1 in dyz, 1 in dz square, and 1 in dxy. Now you can ask a question, why the electrons are not going to dx square minus y square? Because we know that the energy gap is too high to make those electrons to jump into dx square minus y square. Now you can see all the orbitals contains not a single occupied orbitals. All orbitals contains either 2 electrons or no electrons. So there is no single occupied orbital. That's why square planar in this D8 configuration square planar complex is diamagnetic, and you can see most of the square planar complexes, they are diamagnetic, because you can find only D8 configurations in square planar complexes most of the time. Thank you for watching the video. Welcome to another video lecture on coordination chemistry. I am Dr. Jinesh. I am from Department of Chemistry, Ramaiah University of Applied Sciences. We studied the splitting of d orbitals in the previous video lectures, and the splitting in octahedral field is shown in this figure. So splitting of d orbitals in an octahedral crystal field with the energy changes measured with respect to the barycenter, the energy level shown in the hashed line. We studied the factors affecting the value of delta octahedral in the previous video lectures. magnitude of delta octahedral is the strength of the crystal field, and the extremes of the crystal fields are termed as strong field and weak field. So delta octahedral for weak field will be lesser than that of delta octahedral of strong field. In the previous video lecture, we studied the value of delta octahedral can be determined by electronic spectra using UV visible spectroscopy. For example, consider the D1 complex TiOH263 plus. The ground state is represented as T2G1 Eg0, because only one electron is present in the d orbital, that will be in T2G orbital, because the energy of T2G orbital is lesser than that of Eg orbitals. Now, when a radiation is passed through the above complex, the complex absorbs a portion of the radiation to transfer that electron from T2G to Eg, and the amount of energy required for this transition depends on the energy gap between T2G and Eg, which is delta octahedral. The absorption spectrum of this complex ion is shown in figure 2, which exhibits one broad band for which delta maximum is around 20,300 cm raised to -1 wave number, corresponding to an energy change of 243 kJ per mole. The conversion we studied already in our previous video lecture. 1 cm raised to -1 wave number equal to 11.96 into 10 to the power -3 kJ per mole. The absorption results from a change in electronic configuration from T2G1 Eg0 to T2G0 Eg1. That means the electron present in T2G is now in Eg, and the value of delta max gives a measure of delta octahedral. For system with more than 1d electron, the evaluation of delta octahedral is more complicated. It is important to remember that delta octahedral is an experimental quantity. Now we will study the factors governing the magnitude of delta octahedral. There are mainly three factors affecting the magnitude of delta octahedral in a coordination complex. They are: 1. Nature of or identity of the metal atom or ion, oxidation state of the metal atom or ion, nature of the ligand, whether it is strong or weak. For octahedral complex, delta octahedral increases along the following spectrochemical series of ligand. The spectrochemical series is given here. You can see that in the series, the position of iodide is the least, where the octahedral value increases to bromide, to NCS, to chloride, to fluoride, to OH minus, and towards cyanide, the delta octahedral increases. That means from weak field ligands such as halides to strong field ligands such as carbonyl or Cn minus, delta octahedral value increases. Here you can see NCS are in two positions. The reason because NCS ligand is an ambidentate ligand. The NCS minus ion may coordinate through N or S donor, distinguished in red color. When you can see in S, red color means the linkage is happening through sulfur. If the red color is on N, then the linkage is through nitrogen, and accordingly it has two positions in the series. Now you can see ligand with the same donor atom, similar donor atoms are close together in the series. You can see iodide, bromide, chloride, fluoride. They are all halides, and they are very near in the spectrochemical series. Trends in the value of delta octahedral lead to the conclusion that metal ions can be placed in a spectrochemical series which is independent of the ligand. Now you forget about the ligand, now you consider only about the metal ion. Metal ion also influences the ligand strength, and you can see irrespective to the nature of the ligand, the field strength, the crystal field strength increases for the metal ions in this order, like from manganese 2 to nickel 2 to cobalt 2 to Fe3 to chromium 3. You can see in this order the field strength of the coordination complexes involving these metal ions, irrespective to the nature of the ligands, increases. Now, spectrochemical series are empirical generalization, and simple crystal field theory cannot account for the magnitude of delta octahedral value. So, it is not easy to theoretically predict what will be the delta octahedral value for the complexes, because the spectrochemical series is just an empirical generalization. Now we will study the crystal field stabilization energy for high and low spin octahedral complexes. We now consider the effects of different numbers of electrons occupying the d orbitals in an octahedral complex. Now you can see the splitting of the d orbitals, and we know that the splitting in an octahedral field happens like this: dxy, dxz and dyz, and we named as T2g orbitals, and dz square and dx square minus y square, we termed them as Eg orbitals, and the difference in the energy we call it as delta octahedral, and the energy, the line that you can see here, the dotted line, that is known as barycenter, and from the barycenter to the T2g orbital, the energy value is minus 0.4 octahedral, and from the barycenter to the Eg orbital, the energy we can put it as plus 0.6 delta octahedral. Now, you consider a D1 configuration. D1 configuration means only one electron is present in the d orbital. Then, as per the system, that electron in the ground state should occupy at the T2g orbital. So, with respect to the barycenter, now there is a stabilization energy. We can calculate the crystal field stabilization energy as number of electron, that is 1 into T2g. In T2g, what is the energy value? Minus 0.4 octahedral. That means for D1 configuration, the crystal field stabilization energy value is minus 0.4 octahedral. How that value comes? Only one electron in T2g. T2g, the energy value of one electron in T2g is minus 0.4 octahedral. Now you consider a D2 configuration. So at ground state, the D2 configuration means the two electrons will be in T2g. So 2 electrons are in T2g. In T2g, the value of energy is minus 0.4 or delta octahedral. So crystal field stabilization energy equal to number of electron, which is 2 into minus 0.4 delta octahedral equal to minus 0.8 delta octahedral value. So the crystal field stabilization energy for D2 configuration is minus 0.8 delta octahedral. Now consider D3 configuration. In D3 configuration at ground state, the electronic configuration will be T2g3. So crystal field stabilization energy we can calculate 3 into minus 0.4 delta octahedral equal to minus 1.2 delta octahedral. Now you consider D4 configuration. In D4 configuration, two types of configurations are possible. One, all the 4 electrons are in T2g, or 3 electrons are in T2g and 1 electron in Eg. So for a ground state D4 electron, 2 arrangements are possible. The 4 electrons may occupy in the T2g set with the configuration of T2g4, or may singly occupied 4 d orbitals such as T2g3, Eg1, given as like in the figure. Now you see the configuration 20.3, which corresponds to a low spin arrangement. You can see a low spin arrangement, and 20.4 to a high spin arrangement. The preferred configuration is that with the lower energy and depends on whether it is energetically preferable to pair the fourth electron or promote it to the Eg level. So two cases, the preferred configuration is that, which one is preferred configuration is that with the lower energy and depends on whether it is energetically preferable to pair the fourth electron or promote it to the Eg level. So which is preferred configuration, that depends on the metal ion as well as the ligand. So either it can prefer all the electrons, let it be there in T2G, or the singly occupied in all the orbitals of T2G and one orbital in Eg. If a forced pairing, that means all the electrons are in T2G, that means energetically preferable to pair the fourth electron to the T2G, then electron pairing energy is also coming into the picture. We call it as a term P, which is the energy required to transform two electrons with a parallel spin in different degenerate orbitals into spin paired electrons in the same orbital. So in the configuration 20.3, the fourth electron went into the orbital with an opposite spin. So here another energy term will be involved, and that energy term is known as electron pairing energy P. So I am repeating the sentences. Two terms contribute to the electron pairing energy P, which is the energy required to transform two electrons with a parallel spin in different degenerate orbitals into spin paired electrons in the same orbital. The loss in the exchange energy which occurs upon pairing the electron. The Coulombic repulsion between the spin paired electrons. So the electron pairing energy P, which accounts in these two terms, the loss in exchange energy which occurs upon pairing the electrons and the Coulombic repulsion between the spin paired electrons. For a high spin D4 configuration shown in 20.4, so high spin means 4 electrons, 3 electrons are in T2G and 1 electron is in Eg. So CFSE we can calculate 3 into minus 0.4 because 3 electrons are in T2G, plus 1 into plus 0.6 because 1 electron is in Eg. So the total value will be minus 0.6 delta octahedral. For a low spin D4 configuration, which is shown in 20.3, where all the electrons are in T2G, therefore the crystal field stabilization energy equal to 4 into negative 0.4 because all the electrons are in T2G, where the value is minus 1.6 delta octahedral, but that is not over, plus P, because to occupy that electron in the same orbital, extra energy is required, and that energy is known as pairing energy, so P. So for a low spin D4 configuration, the crystal field stabilization energy equal to minus 1.6 delta octahedral plus P, that is pairing energy. So this pairing energy must be included to account for the spin pairing of two electrons. For that high spin complex formation or D4 configuration, we do not have to take the term P because there is no forced or internal pairing happening. Consider D6 ion configuration. So in D6 ion configuration, In a spherical crystal field, one d orbital contains spin paired electrons and each of the 4 orbital is singly occupied. On going to the high spin d6 configuration in the octahedral field, the electronic configuration will be T2G4 Eg2 high spin, because 4 electron will be in T2G and 2 electron will be in Eg. Here no change occurs to the number of spin paired electrons, and the CFSE we can calculate very easily. 4 into minus 0.4 plus 2 into 0.6 equal to minus 0.4 delta octahedral. So we can calculate the crystal field stabilization energy for a D6 configuration in a high spin complex. The value will be 4 into minus 0.4 plus 2 into 0.6 equal to minus 0.4 delta octahedral. For a low spin D6 configuration, the 6 electrons will be in T2G orbital, given rise to CFSE as 6 into minus 0.4 delta octahedral plus, here how many pairing is happening? 2 pairing. So 2p also will be added to the crystal field stabilization energy. So the value will be 6 into minus 0.4 delta octahedral plus 2p. So the value will be minus 2.4 delta octahedral plus 2p. The pairing energy term of 2p, which accounts for the spin pairing associated with the 2 pairs of electrons in excess of the one in the high spin configuration. Now you see the table 20.3 lists the value of CFSE for all DN configurations in an octahedral field, whether it is high spin or low spin. So you can calculate, you can see all the values associated with the DN configuration, all crystal field stabilization energy values associated with the DN configuration, both in high spin or weak field or low spin, strong field configurations. So when the crystal field is weak, we can say for high spin, delta octahedral value will be lesser than P. For a strong crystal field, the delta octahedral value will be higher than P. Now figure 20.6 summarizes the preferences for low and high spin D5 octahedral complexes. So here you can see 2 different complexes of Fe. One is a weak field high spin complexes FeOH26 3 plus and a strong field low spin complex, that is FeCN6 3 minus. Here you can see the difference in the arrangement of electrons in T2G and Eg. We can now relate the types of ligand with a preference for high or low spin complexes. Strong field ligands such as Cn minus favor the formation of low spin complexes, that means all electrons are in T2G, while weak field ligands such as halides tend to favor high spin complexes or OH2 high spin complexes. However, we cannot predict whether high or low spin complexes will be formed unless we have the accurate value of delta octahedral and P. So if the delta octahedral value is higher than that of the value P, then the crystal field will be a low spin complex. Here I give you few self-studies exercise. All of you please try to find the answers of all these questions and let me know the answers. Now we will study the stability constant of coordination complexes. Consider a hydrated complex ion represent the hexa-aqua ion MOH2 6 times and Z plus. Z plus is the charge of this coordination sphere. Now consider the addition of a neutral ligand L to the solution and the formation of series of complexes MOH25L Z plus, MOH24L2 Z plus to ML6 to Z plus. That means it will be a replacement reaction where ligand L will be replacing the OH2 ligand from the hexa-aqua ion. So how many steps will be there? Totally 6 steps. Replacement of 1 OH2 by L. So 6 steps will be there. The reason 6 OH2 groups are present in this hexa-aqua ion. the stepwise displacement of the coordinated H2O by ligand. The first equation will be MOH2 6 times 6Z plus reacting with the ligand, a replacement reaction occur or a displacement reaction occur where one H2O is replaced by the ligand L. So equation will be MOH2 6Z plus L gives MOH2 5 L Z plus H2O. So it is a displacement reaction. The second reaction is the product of the first reaction, that is MOH2 5 L Z plus is again undergoing a displacement reaction with L, forms MOH2 4 times L2 plus H2O. So here again one H2O is replaced with one ligand. In the third reaction, it is continuing. The ligand is replacing one H2O group from MOH2 for L2 forms MOH2 thrice L3, and this will continue until the removal of the last OH2 group from the complex ion and form a new complex Ml6Z+. So there are 6 stepwise displacement reaction for the displacement reaction of this hexa aqua ion MOH2 6Z+. Now, the equilibrium constant for the first reaction, that is reaction number 1, you can write K1. So take the first reaction K1 equal to the product MO concentration of MOH2 5L Z plus divided by the reactant MOH2 6 Z plus L. Normally we won't write the concentration of H2O, we consider it as unity. That's why the equilibrium constant of K1 you can write it as concentration of the product, which is concentration of MOH2 5L Z plus charge divided by MOH2 6 Z plus into the concentration of the ligand. Similarly, you can write for the stability constant or the equilibrium constant K2, K3, K4, K5, K6 for the remaining 6 experiments. So similarly, for the first equilibrium constant K1, you can find the remaining 5 more equilibrium constant until K6 from the given 6 reactions. So together, so it's a 6 stepwise reaction. So together, if you are writing all the 6 reactions into a single reaction, the reaction will be MOH2 6 Z plus 6 ligand gives Ml6 Z plus 6 H2O. Even though the reaction happened in stepwise, we can write the entire reaction using this equation. In order to distinguish stepwise and overall stability constant, the symbol beta is generally used for the overall stability constant. So stepwise stability constants were K1, K2, K3, K4, K5, K6. The overall stability constant is represented as beta. Actually, we won't use the word beta, we will use the word beta 6 because it is the sum of all the 6 reactions. So because the overall stability constant for product of each reactions, we will take beta as 6, and we defined beta 6 as beta 6 equal to ml raised to 6 Z plus. So that is the product of the reaction 8 divided by m of OH2 6 Z plus into concentration of L raised to 6. So the final equation for the overall stability constant, that is beta 6, can be written as the concentration of ML6 of Z plus charge divided by concentration of M OH2 6 Z plus charge into ligand concentration raised to 6. Now we know that the values of K and beta are related. How? The beta 6 will be the product of all the stability constants. So beta 6 we can write it as K1 into K2 into K3 into K4 into K5 into K6. So if you take logarithm, it will be logarithm of beta 6 equal to logarithm of K1 plus logarithm of K2 plus logarithm of K3 plus logarithm of K4 plus logarithm of K5 plus logarithm of k6. So the stepwise equilibrium constant and the overall stability constant, they are related. So concluding this this section, we can write the equilibrium constant, the overall stability constant beta n can be written as the final product concentration divided by the initial reactant concentration into the ligand concentration raised to n. N means how many steps the reaction is happening. So we will conclude this session, and the summary of this session we studied about the weak and strong field and how the electrons will be arranged if it is in a strong field or if it is in a weak field, and also we studied about factors governing the magnitude of delta octahedral. Then we studied about the crystal field stabilization energy, high and low spin octahedral complexes by taking D1, D2, D3, D4, D5 and D6 configurations. Then we studied about the stability constant of coordination complexes, and we derived an equation for the overall stability constant beta 6, and we already studied the relationship between the stepwise stability constant and overall stability constant.